growing scarcity of clean fresh water worldwide is causing a water crisis. 1 in 9 people lack access to safe drinking water, and as a result, a child dies every minute from a water-related disease. On top of that, women and children spend an average of 140 million hours a day collecting water. With 97.5% of the world's water being salt water, it would be great to be able to turn to that as a source of clean, fresh, potable water. But how?
Osmosis. Osmosis allows for water highly concentrated with salt to be turned into fresh water. Forward osmosis achieves this by osmotic pressure causing water to diffuse across a semi-permeable membrane from a lower concentration of salt to a higher concentration. Reverse osmosis, on the other hand, uses high pressure to overcome the osmotic pressure to force water through the membrane, leaving the salt behind. While both have pros and cons for various desalination and water purification applications, they can often work together in a system as complementary processes. Regardless, both of these methods offer a part in the solution to a growing water crisis.
Forward osmosis. First, the drawn feed tanks are filled with 2 liters each of DI water, making sure all lines are disconnected while doing so. All fittings are then connected. The chiller level must be checked and filled if need be. The chiller is then turned on and set to the proper temperature, between 19.3 and 19.8 degrees Celsius. While the chiller reaches the desired temperature, the membrane may be placed in the cell using gloves. Make sure to know orientation and that its edge lies between the inner and outer O-ring. Once the cell is bolted shut, the pumps can be turned on and the flow rate can be set. The software can then be started and equilibration may begin. Once the system weight has equilibrated, the desired amount of salt solution can be added to the draw tank. The system must again equilibrate as water permeates the membrane. This may take up to 50 minutes. Once the weight change becomes negligible, the conductivity of the feed tank is measured and recorded along with the weight of the draw tank. After the data has been collected, the system must be flushed twice with tap water and a third time with DI water. Lastly, the system must be air purged.
Reverse osmosis. Since the chiller is already on and at the desired temperature, the chosen membrane can be added to each cell, making sure to add a small amount of DI water to the cell first and orienting the membrane so that the shiny side is face down. The top half of the cell can then be bolted closed. Next, the feed tank must be filled with 9 liters of DI water. The pump can then be turned on, making sure any bubbles in the system are shaken out so they do not enter the pump and cause cavitation. Once the system is flowing smoothly, the desired pressure and flow rate may be set using the needle valve and pressure regulator. At this point, 1 liter of salt solution is added to the feed tank. The system is allowed to equilibrate for about 10 to 15 minutes. Tests can then be performed by collecting the permeate in 3 graduated cylinders, 1 for each cell. The conductivity of the permeate in each graduated cylinder is measured and recorded, along with the volume of the permeate collected within a certain amount of time. After all tests are performed, the system must be flushed twice with tap water and once with DI water. The system is then air purged and the membranes can be removed, checked for imperfections, and discarded.
For forward osmosis, we tested the CTA membrane with smooth side down, a constant applied pressure of 5 psi, and a constant flow rate of 1 liter per minute. We varied the draw concentration between 0.05 and 0.2 molar salt solution. The water flux is plotted here against the effective osmotic pressure gradient and against the effective concentration gradient. The membrane permeability, A, is determined by the slope of the line as defined by the governing equation for forward osmosis water flux. The salt flux is plotted against the effective concentration gradient. The salt water permeability, B, is determined by this slope, as defined by the governing equation for forward osmosis salt flux.
For forward osmosis, we also tested changing flow rate between 1 and 2.5 liters per minute. Changing flow rate did not have an effect on the concentration or pressure gradient, but did have an effect on water and salt flux, so we plotted water and salt flux against flow rate. There is no relationship between these and the membrane or salt water permeability constants, so nothing can be said about the slope of the line. For reverse osmosis, we tested 3 membranes. NF90, NF270, and BW30. We varied pressure from 1,000 kilopascals to 2,000 kilopascals, and held flow rate constant at 3 liters per minute. The water flux is plotted against transmembrane pressure. The membrane permeability, A, is defined in the equation for reverse osmosis water flux and determined by the slope of the line. Salt flux is plotted against the effective concentration gradient. As with forward osmosis, the equation for reverse osmosis salt flux defines the salt water permeability B, which is given by the slope.
For forward osmosis, we found that CTA has a membrane permeability of only 0.423 LMH per bar and a salt water permeability of 4.699 times 10 to the negative 7th meters per second. However, due to outliers and a lack of abundant data, we do not find our values to be conclusive.
As for our reverse osmosis membranes, NF270 had the highest membrane and saltwater permeability, while BW30 had the lowest membrane and saltwater permeability. Both BW30 and NF90 showed comparably high salt rejections, averaging 91.9% and 91.6% respectively, while NF270 was around 41% salt rejection. Salt rejection values reported by Dow Water and Process Solutions support our results for the NF90 and NF270 membranes.
We conclude that NF90 is the best performing reverse osmosis membrane. It is just about tied with BW30 for the greatest salt rejection, while its membrane permeability is more than double that of BW30, meaning more permeate can be collected in a given amount of time. Thus, NF90 wins in both quality and efficiency, both of which are key to an important industrial process such as reverse osmosis.